Welcome back. Today we will be diving into Chapter 4 of Backend Web Development. Chapter 4 is titled Web Servers and APIs. Introduction to Web Servers. Web servers are foundational components of the Internet infrastructure, responsible for delivering web content and services to users worldwide. In this section, we delve deeper into the role and functionality of web servers, their architecture, and the protocols they use. Role of web servers. Web servers serve as intermediaries between clients, such as web browsers and web applications or websites hosted on remote servers. When a user requests a web page or resource, the web server receives the request, processes it, retrieves the necessary data, and sends back the response. This process enables users to access and interact with web content seamlessly. Functionality of web servers. At their core, web servers are software applications designed to handle hypertext transfer protocol, HTTP requests from clients. They utilize a variety of modules and components to interpret requests, execute scripts or applications, and generate dynamic content. Additionally, web servers support other protocols such as secure HTTP, HTTPS, File Transfer Protocol, FTP, and Simple Mail Transfer Protocol, SMTP, enabling diverse functionalities beyond serving web pages. Architecture of web servers. Web servers typically follow a client-server architecture, where clients initiate requests and servers respond with the requested content. Modern web servers often adopt a multi-process or multi-threaded model to handle concurrent connections efficiently. They may also employ caching mechanisms, load balancing, and reverse proxying to enhance performance, scalability, and reliability. Types of web servers. Apache HTTP Server and Nginx are among the most widely used open-source web servers, powering millions of websites globally. Apache, known for its flexibility and extensibility, supports various programming languages and modules, making it suitable for diverse use cases. Nginx, on the other hand, is renowned for its high performance, scalability, and efficient handling of static content and concurrent connections. Setting up and configuring web servers, e.g., Apache and Nginx. Web servers are the backbone of the Internet, responsible for delivering web content and applications to users across the globe. In this section, we delve into the process of setting up and configuring two of the most widely used web servers, Apache HTTP Server and Nginx. Apache HTTP Server. Apache is an open-source web server software renowned for its reliability, flexibility, and extensive feature set. Setting up Apache involves several steps, starting with installation and configuration. Installation. Apache can be installed on various operating systems, including Linux, Windows, and Mac OS. On Linux distributions like Ubuntu and CentOS, Apache can be installed using package managers such as apt or yum. Windows users can download and install the Apache binaries from the official Apache website. Configuration files. Apache's main configuration file, httpd.conf, contains directives that define server behavior, such as listening ports, virtual hosts, and access control rules. Additional configuration files, such as ssl.conf for SSL TLS settings and httpd vhosts.conf for virtual host configurations, may also be used. Virtual hosts. Virtual hosts allow Apache to serve multiple websites from a single server by mapping domain names to specific directories on the file system. Each virtual host configuration includes directives for specifying document routes, server aliases, log files, and more. Modules and extensions. Apache supports a wide range of modules and extensions that extend its functionality. Common modules include mod rewrite for URL rewrite SSL for SSL TLS support, and mod proxy for reverse proxying. Nginx. Nginx is a lightweight, high-performance web server and reverse proxy known for its efficiency and scalability. Setting up Nginx involves similar steps to Apache. Installation. Nginx can be installed from the official package repositories on Linux distributions or downloaded as precompiled binaries. Package managers like apt and yum simplify the installation process on Debian-based and Red Hat-based systems, respectively. Configuration files. Nginx's main configuration file, nginx.conf, is typically located in the /nginx directory. This file contains directives for configuring server blocks, upstream servers, SSL TLS settings, and more. Nginx follows a modular architecture, allowing additional configuration files to be included via the include directive. Server blocks. Nginx uses server blocks to define virtual hosts, similar to Apache's virtual hosts. Each server block includes directives for specifying server names, document routes, access control rules, and error pages. Reverse proxying. Nginx excels at reverse proxying, a technique used to forward client requests to backend servers. By configuring proxy pass directives, Nginx can proxy requests to applications running on different ports or servers, enabling load balancing and application isolation. Best practices and security considerations. Regardless of the web server chosen, there are several best practices and security considerations to keep in mind. Regular updates. Keeping the web server software and operating system up to date is essential to address security vulnerabilities and ensure optimal performance. Security hardening. Implementing security best practices such as configuring firewalls, enabling HTTPS encryption, and limiting access to sensitive directories helps mitigate security risks. Monitoring and logging. Monitoring server logs and performance metrics allows administrators to identify and address issues promptly, ensuring the reliability and availability of web services. Load balancing and scalability. Web servers can be deployed in clustered or load-balanced configurations to distribute traffic across multiple servers and improve scalability and fault tolerance. Developing and consuming APIs. Application Programming Interfaces, APIs, play a crucial role in modern software development, enabling communication and interaction between different software systems. In this section, we explore the process of developing and consuming APIs, covering key concepts, best practices, and common techniques. Introduction to APIs. APIs define a set of rules and protocols that allow different software applications to communicate with each other. They provide a way for developers to access and manipulate data or functionality exposed by a web service or application. APIs can be categorized into several types, including web APIs, RESTful or SOAP, library APIs, and hardware APIs. Developing APIs. Developing an API involves designing, implementing, and exposing endpoints that clients can interact with. Key considerations in API development include design. API design focuses on defining endpoints, request-response formats, authentication mechanisms, and error handling. RESTful APIs adhere to principles such as statelessness, uniform resource identifiers, URIs, and HTTP methods, get, post, delete. Implementation. API implementation involves writing code to handle incoming requests, process data, and generate appropriate responses. Developers choose programming languages and frameworks based on factors like performance, scalability, and ecosystem support. Documentation. Comprehensive documentation is essential for API adoption and usability. API documentation typically includes information about endpoints, request-response formats, authentication methods, error codes, and usage examples. Testing. Thorough testing is crucial to ensure API reliability, security, and compatibility. Unit tests, integration tests, and end-to-end tests validate API functionality, data integrity, and error handling under different scenarios. Consuming APIs. Consuming an API involves making HTTP requests to access resources or invoke functionality exposed by the API. Key considerations for API consumers include authentication. Many APIs require authentication to authorize access to protected resources. Common authentication methods include API keys, OAuth tokens, and JWT, JSON Web Tokens. Request format. API consumers must understand the request format of the API, including HTTP method, headers, parameters, and payload if applicable. Tools like curl, Postman, and Swagger UI facilitate API exploration and testing. Response handling. API consumers parse and process the response received from the API server. Handling different response status codes, e.g., 200 OK, 404 not found, 500 internal server error, and extracting relevant data from the response payload are essential tasks. Error handling. Effective error handling is critical for robust API consumption. API consumers should anticipate and handle errors gracefully, including network errors, server errors, and application-specific errors returned by the API. Best practices and considerations. Designing APIs with simplicity, consistency, and clarity improves usability and reduces integration efforts for consumers. Versioning APIs allows for backward compatibility while introducing new features or breaking changes. Implementing rate limiting and throttling mechanisms protects API servers from abuse and ensures fair usage by consumers. Monitoring API usage, performance, and errors helps identify issues and optimize resource allocation. RESTful API design principles. Representational state transfer, REST, is an architectural style for designing networked applications, especially web services. RESTful APIs adhere to certain principles and constraints to promote simplicity, scalability, and interoperability. In this section, we delve into the key principles of RESTful API design and their significance in building efficient and maintainable APIs. Resource-oriented design. RESTful APIs model resources as the fundamental entities that clients can interact with. A resource represents a concept or entity in the application domain, such as users, products, or orders. Each resource is identified by a unique URI, Uniform Resource Identifier, and clients manipulate resources using standard HTTP methods: GET, POST, PUT, DELETE. Stateless communication. RESTful APIs are stateless, meaning that each request from a client to the server contains all the information necessary to process the request. The server does not maintain any client state between requests. Stateless communication simplifies server implementation, improves scalability, and enhances fault tolerance. Uniform interface. The uniform interface constraint of REST ensures consistency and simplicity in API design. Key principles of the uniform interface include resource identification, resource manipulation, and representation. State transfer. RESTful APIs transfer state between clients and servers through representations of resources. Clients retrieve, create, update, or delete resource representations using HTTP methods. Responses from the server contain the requested resource representation, along with metadata like status codes, headers, and hyperlinks to related resources. Hypermedia as the engine of application state, HATOS. HATOS is a principle that emphasizes the use of hyperlinks within resource representations to navigate the application state. In a HATOS-compliant API, clients discover and interact with resources dynamically by following hyperlinks provided in responses. HATOS promotes decoupling between clients and servers, enabling server-driven application flow and evolution. Layered system. RESTful APIs are designed as layered systems, where different components, e.g., client, server, caching layer, operate independently and interact through well-defined interfaces. Layering enhances scalability, modifiability, and interoperability by separating concerns and promoting encapsulation. Cacheability. RESTful APIs leverage caching to improve performance, reduce server load, and minimize network latency. Responses from the server include cache control directives that specify whether and for how long the response can be cached by clients or intermediary caches. Caching can be implemented at different levels, including client-side, server-side, and intermediary caches. Stateless authentication and authorization. RESTful APIs authenticate and authorize clients on a per-request basis without relying on server-side sessions or cookies. Authentication credentials, such as API keys or OAuth tokens, are included in request headers or query parameters. Stateless authentication simplifies client-server interactions and enhances security by eliminating the need for server-side session management. Stay tuned as we continue to dive deep into the study. See you soon.